There's this new technology from Google that's quietly changing the fundamental economics of AI. And it's not what you think. It's not a new model, it's not a new chip. It's a compression algorithm called TurboQuant, and it's tackling one of the biggest hidden costs holding AI back.
All right, so here's how we're going to break this down. First, we've got to understand the massive memory problem that AI is facing. Then, we'll dive into how TurboQuant's clever math provides a solution. And finally, the really exciting part, what this means for the future of AI, from smarter agents all the way to the new economics of the entire industry.
Okay, so to really get a handle on this, we first need to talk about the real wall that AI is hitting right now. And, spoiler alert, it's not just about building bigger brains. So I want you to think about this for a second. When we talk about what's holding back AI systems like Gemini or GPT-4, when you're actually using it, what do you think the real bottleneck is?
Yep, it's memory, plain and simple. The real headache isn't the thinking, it's moving and storing all the data. The more stuff an AI needs to remember, the more memory it eats up, and that gets crazy expensive super fast. And at the heart of this whole mess are these things called vectors. You can think of them as the language of AI. These super long strings of numbers that represent, well, everything. Words, images, you name it. The problem is AI uses them for everything. It's the AI's short-term memory, that's called the KV cache, which keeps track of your conversation. It's also the long-term memory for looking stuff up. The more you chat with an AI, the more of these vectors it has to juggle. And that's exactly where your memory costs just explode.
So, if these vectors are the big problem, what's the solution? Well, this is where Google's new trick, TurboQuant, enters the picture. It was built specifically to attack this memory problem head-on.
So, meet TurboQuant. It's what's called a quantization technique, which is really just a super fancy way of saying it's an extreme compression method. The whole goal is to shrink down those memory-hogging vectors, but, and this is the absolute key, without messing up the model's performance. So how does it actually pull this off? It's a really slick two-step process. First, you've got an algorithm called PolarQuant that does the heavy lifting. It efficiently compresses the main signal of the vector. But then, a second algorithm called QJ swoops in and cleans up any leftover errors with this tiny little one-bit trick. It's genius, really. It makes sure the final result is still incredibly accurate.
And this slide really helps explain the cleverness behind PolarQuant. Think about giving directions. You could say, go 3 blocks east, then 4 blocks north. That's standard coordinates. Or, you could just say, go 5 blocks in that direction, and point. That's polar coordinates, a distance and an angle. It turns out, this is a way more efficient way to describe vectors, and it dodges a ton of the hidden memory overhead that older methods get stuck with.
Okay, so we've got this super efficient compression method. Cool. But what does that actually mean for the giant language models we're all using every single day?
And this just lays it out perfectly. Before TurboQuant, if you wanted an AI to read a huge document, you were looking at skyrocketing memory costs. You'd probably need more expensive hardware. But after TurboQuant, you can throw massive amounts of context at it on the same hardware for a tiny fraction of the cost. It basically makes long context AI something that's actually, affordable.
And the results are just wow. In Google's own tests, they did these needle in a haystack tasks where the AI has to find one specific fact in a huge document. TurboQuant slashed the memory needed for that key value cache by at least 6 times. And it did it with perfect accuracy. And it's not just about saving memory. It's also about speed. Look at this chart. On those high-end H100 GPUs, TurboQuant was up to 8 times faster at a really critical calculation called attention logits. That's basically the core process where the model decides what information is important while it's thinking. When there's less memory to wade through, it can make those decisions way, way faster. Now, this gets even cooler when we start talking about AI agents. Agents are kind of the next big thing, right? They do complex, multi-step tasks. And they get hammered by memory costs twice, once for their own internal thinking and a second time when they have to go look up information.
So for the folks building these agents, the benefits are just massive. You're talking cheaper long-term memory, a much bigger scratch pad for the agent to work through problems, and way faster memory retrieval. It means you can run more agents at the same time on the same hardware. And it even makes running powerful agents on your phone or laptop a much more realistic idea.
And this creates this incredible ripple effect. I mean, making one agent cheaper to run is great, sure, but think bigger. The idea of building systems with lots of agents all working together, like a specialized team tackling a problem, That goes from being a wildly expensive dream to something that's suddenly very practical. All right, let's zoom out to the really big picture here, because this isn't just some small tweak. This fundamentally changes how the entire AI industry thinks about building and scaling these systems.
Right, and this quote really nails it. For the longest time, the solution to every AI problem was just throw more expensive hardware at it. TurboQuant is this powerful reminder that actually, smarter algorithms and better engineering can unlock huge gains without just writing a bigger check. The math matters again.
So here's the bottom line. This is what actually changes. Long context AI, suddenly affordable. Those RAG systems that let an AI look stuff up before answering, they get cheaper and way more efficient. Product teams can now afford to let their AI tools remember way more about your past conversations. And maybe most importantly, it starts to level the playing field a bit, chipping away at the massive hardware advantage that only the biggest companies used to have.
So, to be super clear, this doesn't make the AI itself smarter. TurboQuant is a breakthrough in systems and compression, not in reasoning. But its impact is massive because it makes running the most advanced AI much cheaper and more accessible for everyone.
And that leaves us with a really interesting question to chew on. For years, we've all been obsessed with the size of these AI models. But what if the next great race in AI isn't won by the team that builds the biggest model, but by the team that comes up with the smartest math to run it?